It's recording. Okay. Welcome to the CERIAS Computer Security Seminar from Purdue University. Our speaker today is Professor Ian Goldberg from the University of Waterloo, and he will talk about Sphinx, a compact and provably secure mix format. Okay, Ian.
Thank you very much.
That's my seat.
Okay, this is joint work with George Dinazis of Microsoft Research, and if you want more information about what I'm going to be talking about today, this was a paper in the IEEE Symposium on Security and Privacy a few months ago. So I'm going to be talking about first mixed networks, what they are, then mixed formats, a particular aspect of mixed networks. I'll be talking about Sphinx in particular, the mixed format that we'll be presenting, do a brief outline of its proof of security, and then conclude. So first off, what is this mixed network thing? You may not have heard of it. So the idea of a mixed network is to enable a user, say Alice, to be able to send messages over the internet without automatically revealing her identity or her location. Okay? So why might we want to do this? Well, this is good for a number of reasons. For example, people who want to discuss sensitive topics, something like sexual assault survivors or cancer survivors, support groups, stuff like that. Whistleblowers who want to protect themselves against retaliation. So you're an employee at a company, you want to notify somebody that your company is leaking toxic waste into the river over here. You want to do that without your company finding out that you're talking to the Environmental Protection Agency, for example. Quite recently, we saw examples of this latter, where reporters or dissidents or citizens in certain countries might want to be protected when they communicate with people outside. So we saw this happening in Myanmar in 2007, and we saw it happening very recently, just in June, in Iran. Okay, we had people talking, wanting to communicate and getting their message out, where the people who run the network, the government or people controlling the communications in some way, are the people they want to protect themselves from. Okay? So, a simplistic solution that was used in the early 90s is just to send a message to a trusted friend and have that friend strip off your name and forward it on for you. Okay? And it doesn't have to be a friend, it could just be some person running a service that does this. So, as I said, this was used in the early 90s, and the problem is that this requires that the relay is trusted. So if you do this, send it to the relay strips off your identifying information and sends it on. This has the problem that the relay itself knows who you are and who you're talking to and what you're saying. Okay? And this can be an issue. One of these relays that was used in the 90s was called a non-penet phi. And that the 90s might be before some of your times. I guess if you're grad students, you might be familiar with this. Freshmen this week probably would not be familiar with this. But what happened was, so a non-penet phi allowed you to send messages through it, and whenever I sent an email message through it, it would see my name, check a list, and if I'm not already in the list, it would add me to the list and assign me a random number ID, so a non-25549 at a non-penet phi. Okay? And then it would send the message, making it look like it came from a non-25549 at a non-penet phi. That way, replies to the message would go to a non-penet phi would say, oh, this is a reply to a non-25549, looks up in the list, oh, it's Ian, and here's his real address, and it will send the reply to me. So a non-penet phi had to maintain this list, this mapping, between real people, real email addresses, and they're anonymous pseudonyms. Okay, they're pseudonyms anon25549, whatever. Okay, so what happened in the 90s was that somebody used anon-pennet-phi to send some work from a certain church that will not be named, that you might know who it is, and that church claims copyright over their scriptures. And anyone who posted those scriptures to the internet kind of got in trouble. And so someone did it anonymously, and they wanted to find out who it was. So they sued Johan Helsingus, the operator of anon-pennet-phi, and in court tried to get him to turn over this list. And Johan luckily managed to prevent the turning over of the entire list, but could not prevent the turning over of just the 2 addresses in question. Okay, so he had to turn over part of this list. And then he just shut down his service because he said, if I can't protect my users against an attack like filing a lawsuit, then I'm not going to run the service, because I can't, in good conscience, run the service when I know my users could be outed very easily. As it happens, the users of this service, in this particular case, were a little bit clever, and the addresses that were turned over were just addresses of other remailers. So in fact, this idea of using multiple remailers is a good solution to this problem. So instead of sending the message just through one relay, we send it through a whole path of relays. Okay? And this alleviates not only the trust problem, but also other network issues like load balancing. So not all messages over the internet are going through this one central point. Right? So let's look at a picture of how mixed networks work. So here we have a picture of Alice and Bob. And these swirly things in the middle are meant to represent mixed nodes. So there are a number of mixed nodes, which are servers spread throughout the internet. Alice wants to send a message to Bob without revealing to Bob her identity or her location. So what Alice does is she picks a number of mixed nodes to form what's called a path. Okay, in this case, Alice picks 3 mixed nodes that you may be able to see in yellow, but the arrows point them out. And then Alice constructs her mixed message. And her mixed message contains basically her message wrapped in a layer of encryption, wrapped in another layer of encryption, wrapped in another layer of encryption. Okay? And we're going to visually represent this encryption by envelopes, as is often done. So Alice ends up with this envelope, and inside this envelope is another envelope, and inside that envelope there's another envelope, and inside that there's the message. Okay? So Alice takes this envelope and sends it on to the first mixed node. That mixed node opens up the envelope and pulls out what's inside. It's another envelope, and that envelope is addressed, and that envelope is addressed to the next remailer. So it sends it on to the next one, who opens it up and finds another envelope, and that envelope is addressed to someone else, that being the next remailer. So it sends it on. That remailer opens up that envelope, finds a plain message that is also addressed, and it's addressed to Bob, and it sends that message on to Bob. Okay? So that's how a mixed message at a high level gets from Alice to Bob. Now Bob, of course, just receives this message from Alice, from the last mixed node, and doesn't know that it came from Alice. Okay? Great. So, that last picture you just saw, some of you may have seen a very similar picture in another context, and that's of onion routing, or you may know Tor. Okay? Some people are nodding, they know about Tor, maybe you've used Tor. So what's the difference between what I'm talking about here and Tor? So the big difference is that Tor is meant to handle real-time traffic. Okay? So what happens in Tor is that between Alice, the client, and Tor is meant to communicate from clients to things like web servers rather than people. So between Alice and a web server, in this case Bob is a web server, a interactive bidirectional link is set up. Okay? So it's not just that a message is sent and then something sent there and something sent there and on, but rather a real-time interactive nested encryption tunnel is set up that allows packets to travel in approximately real time through the internet, being decrypted, nested decrypted one way and nested encrypted the other way. Okay? And this is great for real-time requirements like World Wide Web and instant messaging and stuff like that, right? It would be bad if when you fetched a web page, it took like an hour to come down. Or if you're having an IM chat with someone and it takes an hour for each message to get there, or worse, a day, right? That would be ridiculous. That said, in the early days of the web, there were systems before like most people had computers. There were systems that would allow you, this is a digression, but it's funny, so. There were systems that you would, they would fax you a web page, and next to every hyperlink there would be one of those little mark circles like you take on exams, and you'd mark the ones you were interested in clicking and you'd fax it back to them. And then they would fax you the pages that result from clicking those links and so on. So, and this was all automated. So that's about as high latency as you want, as you can deal with for web traffic. So Tor handles it quicker than that. On the other hand, what do mixes do? In a mix, each mix node collects the messages that are sent to it and then holds on to it and waits for some amount of time or for some condition to hold. And we'll talk a little bit more about this in a bit. But it holds on, gathers a bunch of messages together, and then opens up all the envelopes, shuffles them into a random order, and sends them on. And that shuffling is what we call mixing. And the goal of the mix node is to prevent someone who's watching the network from being able to see, oh, these messages came into the mix node and these messages came out, and being able to figure out which incoming message corresponded to which outgoing message. Okay? So that's the job of the mix, and that's something we'll spend most of our time on today. How does the mix make sure that you can't link incoming messages to outgoing messages? But because it's holding on to messages for some amount of time, you can't use it for real-time traffic, like World Wide Web or instant messaging, but you can still use it for traffic that's not so time sensitive. Things like email and things like blogging and things more recently like microblogging, like Twitter, right? It's not so vital that your tweets make it online right now if what you're doing is you're tweeting about what's going on the ground in Iran during the protests, right? It's okay if it's delayed by an hour or so, or even a day, as long as the message comes out and they can't identify that you're the one that sent it. Okay? So, mixed networks have two major pieces. The first piece is what I mentioned just a bit ago, the mixing strategy. So as messages arrive at a mix node, how does the node determine how long to wait before processing it? Okay? So some simple mixing strategies are wait until you get 100 messages, then process them and send them all on. Or wait for an hour, and however many messages you get in this hour, you process them and send them on. Or you can do something called a pool mix, which is wait until you have 100 messages, then pick a random 50 of them and send those on, and the other 50 just wait in the pool until you get 50 more, bringing you up to 100, and then you select a random 50 and send them on. Okay? That turns out to have a lot of nice features. There are lots of different mixing strategies. Some of them allow the user to communicate some preference. For example, you might want to tag a message with, this message is needs to be really secure, and I don't care if you hold on to it for extra time if you think it'll add security. Or the user might tag the message with the opposite, saying, put this through as quickly as you can, my privacy is a little bit important, but not so important. Okay? And that those parameters to the mixing strategy will come back later on in the talk. So just remember that there are lots of different mixing strategies, and many of them have certain parameters that the user can communicate. Okay? Other than that, I'm not going to talk more about mixing strategies in this talk. This talk is about the other attribute of a mixed network, the mixed format. Okay? So, as I said, there are lots of mixing strategies out there, all with their pros and cons. The other half is the mixed format. The mixed format is the sort of the byte level description of the mixed message. Exactly what do you encrypt? Exactly what fields do you put in your message? How big is the message? Right? And the important property of the mixed format is that it's exactly what keeps an attacker from linking up the incoming messages to the outgoing messages. Okay? For example, take a really naive mixed format where all you do is you take the message and you just public key encrypt it 3 times. Okay? There are several things wrong with this. First of all, what about messages of different sizes? So a small message comes in, and a medium-sized message comes in, and a large message comes in. And a small message comes out, and a large message comes out, and a medium-sized message comes out. Well, it's pretty obvious which one was which, right? So the mixed format has to hide the lengths of messages. That's one of its jobs. Another one of its jobs is to hide where you are in the path. So for example, if you, again, just did that naive thing, even if you insisted all messages were of constant length, you would have the problem that every time you did a public key encryption, the message would get a little longer, because public key encryption adds some overhead. Okay? So the message would get a little bit longer. So by looking at the size of the message, you'd know where in the path you were. In our envelopes example, if we were to do this in real life with real envelopes, of course, each envelope that you nest inside would have to be a little smaller than the one on the outside. So if I hand you an envelope, you can just measure it and say, oh, this is the 3rd envelope in the sequence. And that's also something we'd like to hide. So things like the length of the path, the position in the path, the next node in the path, and so on. These are all things we'd like to hide. Okay? The mixed format also determines another important property, which is whether Bob can reply to Alice. Okay? Remember how I talked about the anon 25549? That was a mechanism for replies. And it's important that it's at least very useful that a mixed network support the ability for people who receive messages to reply to them. Okay? Otherwise, it's kind of tough to have communication. It's all one way just shouting, right? And no one can have a conversation. So being able to reply to a message that was delivered anonymously so you don't know who it is, who sent it, is quite a useful feature. Now, even if you support replies, it's important for security. It turns out that what you want is that the reply message should look just like any other message in the system, the so-called forward messages. And the reason for this has to do with a concept called the anonymity set. And the anonymity set is basically the number of people using the system or that could have sent this message. So imagine an anonymity system like a mixed network or like Tor where only 10 people in the world use it. Okay? Then if a report out of Iran came from this anonymity system, well, you know who sent it. Well, it's one of these 10 people. Oh, only that one lives in Iran. Well, it didn't provide you much privacy at all. Right? So the more people that use the system, the larger the anonymity set and the better the system protects you. Now, if forward messages and reply messages are handled differently, so if the node, when it's processing a reply message, has to do something different from when it processes a forward message, then basically the forward messages and the reply messages are going through essentially 2 different networks. It's easy for the adversary to just distinguish the forward messages and the reply messages, and now each network only has half as many messages going through it, so the anonymity set is smaller. Okay, so we want to confound things by mixing up the forward messages and the reply messages. Okay, and the mixed format is what we're going to be talking about. Great. So next I'm going to talk about a few mixed formats that exist. So Mixmaster from 1998, this is an established mixed network. It's still out there and in use today. It didn't support replies, and it had what's called heuristic security. And what do I mean by that? Well, often when people design a security system, either a real life like locks and stuff like that, or a computer security system, the way they decide if it's secure is they take the thing and they take a hammer and they hit it with a hammer. Okay? This is metaphorical, of course, in the case of a computer security system, where our hammer are things like cryptanalysis or timing attacks or other things like this. You just take your favorite attack and you hit your new system with it and see if it breaks. And if it doesn't break, you say, okay, great. You take another hammer and you hit the thing with it and you see if it breaks now. No? Okay, I have 20 more hammers in the box and I keep just hitting it with hammers until it either breaks or it withstands all of my hammers. And if it withstands all of my hammers, I say, all right, sounds secure to me. Of course, it might not be. Someone might come up with a new hammer, a new type of attack, and hit it with the new hammer and it might shatter to pieces. You never know, okay? But this is how much of computer security, and in fact, live security, is done today. So this is called heuristic security. So, of course, this doesn't give you the warm fuzzies, right? It's just, you hit it with a bunch of hammers and you failed to break it. It's more your fault than its benefit, right? You're just not smart enough to break the system. So Muller in 03 and Kamenishin and Sky in 05 separately came up with mixed formats that had provable security. And what does that mean? That means there's a mathematical proof that if you can break some aspect of this system, then you could solve some problem believed to be hard, like factoring, right? Or taking discrete logs. Some mathematical problem we believe you can't solve, okay? So follow the logic here. If you could solve this problem, if you could break the system rather, then you could solve a problem we believe to be hard. Okay? So if it really is hard, then the contrapositive, you can't break the system. Okay? So that's called provable security. And it's usually better to have one of these security proofs than to just hit things with hammers. Okay? So we try to do that nowadays. Now, neither Muller or Kamenishin-Lysenskaya's system supported indistinguishable replies. So these were systems that were designed, though neither of them was deployed, that allowed you to send messages, but people couldn't reply to you. MixMinion in 2003 was the first to add support for indistinguishable replies. MixMinion was the follow-up project to Mixmaster, and so it inherited its kind of milieu of heuristic security. But it did add the indistinguishable replies, which was really good. MixMinion is also deployed and in use today. You can go out and use MixMinion right now if you want. Minx was the first to address another problem. It was the first attempt at a compact mix format. Okay? What do I mean by that? Well, all the overhead, the headers you have to do to route a message through this network, they have a certain size. Okay? And we'll see this a little later on. Often the size is in kilobytes. In some cases, in some schemes, it was in the tens of kilobytes. Okay? Which is not very good if your messages are really small. For email, where the messages might be a couple kilobytes, that's maybe okay. But now imagine you were sending tweets. Okay, Twitter messages, 140 byte limit. Do you really want to be sending a 140 byte message with a 2 kilobyte header? That doesn't make any sense. Okay? So Minx was the first attempt at a compact mix format where the size of the overhead was very small. It supported indistinguishable replies, and it was one of these heuristic security things. Unfortunately, it turned out to be broken security. Okay? So what happened was someone hit it with a different hammer, and it shattered to pieces. Okay? Those people then, it was Shimshok, Stats, and Hopper in '08, those people then provided a provably secure fix. So they provided a new version that was kind of similar to Minx, but different in a lot of ways, but it had a proof of security. Unfortunately, which is great, and it still supported indistinguishable replies, but it had this downside, which is very expensive to construct the mixed messages in the first place. And why is that? Remember what I said about the user wanting to communicate information to each mix, right? That might be parameters to the mixing strategy, but for sure it will be the identity of the next mix. Who should I send this message on to? Okay? So there's some amount of information that the user Alice has to share secretly with each mix. In this SSH 08 protocol, the only way that Alice could share information with a mix is for a cryptographic hash of the data to happen to contain the information she wanted to convey. So if she wanted to convey, say, an address, like an IP address, 32 bits, she would have to create mixed messages until one of them happened to hash to that address. And of course, that would take 2 to the 32 times, 4 billion tries, which is crazy. So what SSH 08 said in their paper is that, okay, we're going to say that the only information Alice is allowed to convey is the identity of the next hop, and we're going to say there are at most 255 different mix nodes, and we just store their addresses in a table, and then Alice just has to convey 8 bits of information. Okay? So they get around this expensive to construct mix messages by just saying we're allowed to convey only 8 bits of data per hop. So it still takes 2 to the 8 work, right, times 3, or however long your path is, so times r. But that's not so bad. It's still kind of annoying, okay, and we'd like to do better. So Sphinx, this work, takes the best features of all of them. It has provable security, supports indistinguishable replies, it's compact, and it's computationally cheap, okay? So that's where we're going here. So, let's look at the overhead length. Let's talk about compactness. So here I have a whole bunch of crazy formulas. This chart is taken from the paper. Don't worry, I'll simplify these down to easily comparable numbers in just a minute. So here we have a list of schemes that I've talked about. Their overhead lengths, whether they support indistinguishable replies, and whether their security is heuristic, provable, or in the case of Minx, broken. So what is this overhead length, these crazy formulas? So there are 3 parameters here. The first is R. R, as I mentioned just before, is the maximum length of a path that your system is willing to support. Okay? So common values of R are like 3 or 5 or 10, something like that. Okay? The next one is S. And S is the size of a symmetric key, in this case in bytes. So what should we choose for S? Depends how much security you want. So kind of back when a lot of these systems were being developed, people talked about 80-bit security. So an adversary would have to do about 2 to the power of 80 operations, which is a really big number, in order to break the system. Okay? Now 2 to the 80 is a really big number, but not big enough for some kind of more conservative people. So, and computers are getting faster and can do these operations much quicker. So nowadays we tend to use more like 128 bits or 16 bytes. Okay, so an attacker would have to do 2 to the 128 operations, which is a trillion times harder than 2 to the 80 about. Okay, or even more, 256 trillion. Okay, so that's S. The next part is P. P is the size of a public key. So how do we determine the size of a public key? Well, it depends on two things. One, it depends on the security level you want. Do you want 80-bit security or do you want 128-bit security? Now, if you want 80-bit security, you can't use an 80-bit public key. Reasons, if you've studied cryptography, you probably understand. So for 80-bit security, you might use a 1,000-bit public key if you're using RSA or something like that. The other aspect of the choice of P is exactly what public key system you're using. If you're using something like RSA or Elgamal or Diffie-Hellman, your keys are this big. If you're using something like elliptic curves, your keys are much smaller for the same security. Okay? So that's a benefit of using something like elliptic curves. So I'll give you a couple different parameter selections so you can see how the systems compare. So first, I'll use the kind of traditional numbers mod n, right? Zn star kind of system. So we're talking about RSA, or we're talking about Elgamal or Diffie-Hellman in numbers mod some other big number. So here I've chosen R equals 5, S equals 16, again 16 bytes is 128 bits, so we're talking about the stronger level of security here. I'm talking about P equals 256. Okay, 256 bytes is 2048 bits, and we're going to say that a 2048-bit public key is about the same strength as a 128-bit private key. Now it turns out that's not true. A 128-bit private key is more like a 3000-bit public key, but we're underplaying it here because underplaying it gives an advantage to the other schemes and a disadvantage to ours. So we're being conservative here, okay? And you see, even with that conservative choice of parameter, we still, so Sphinx's overhead is now 448 bytes. It's still quite a bit smaller than any of the others except for Minx, which of course has broken security, so it doesn't really count, right? It's easy to design a really small overhead system that is insecure. Okay, we don't want to use that one. Okay, let's look at another choice of parameters. Here we're going to use elliptic curve cryptography. Again, we're going to use R equals 5 and S equals 16. And now the appropriate size of a public key is 32 bytes, okay, or 256 bits. And that's quite accurate for a 128-bit symmetric key strength. Okay, and here you see Sphinx is smaller than all of the choices except for SSH-08, but SSH-08 has this problem of constructing messages being very expensive. Okay, so we're a little bit bigger than SSH-08, but we don't have this expensive construction problem. If we choose other sets of parameters, such as if we use 80-bit security and R equals 3, we can actually get the overhead of Sphinx down to exactly 100 bytes. And now it's not only comparable to the size of a tweet, it's smaller. So now you might imagine putting the mix header inside the tweet. So you could use Twitter as your communications mechanism for your mix system. And that's an interesting thing that I and my group will be exploring hopefully soon. Of course, the problem there is that your message size is now only 40 bytes. And that's a little small even for tweets, right? So more work needs to be done to see if we can squeeze even a few more bytes out of this header and get it a little bit smaller. But in any case, we're down to something in a reasonable size now. Even for this high security system where we have 224 bytes, that's comparable to the size of a tweet, 140 bytes. It's not like the kilobytes that we saw on the previous slide here, right? Okay, so what actually is the Sphinx message format that I've been talking so much about? Here's where the Greek letters show up. So a Sphinx message consists of 4 parts. The header is alpha, beta, and gamma, and the body or the payload is delta. Alpha is an element of the public key group G. And what is this group G? It's any group satisfying a particular assumption called decisional Diffie-Hellman. And this is just a kind of standard mathematical assumption that we make. It's one of these assumptions like factoring is hard. Okay? It's not that one, but it's a similar one that all of cryptography relies on certain problems being hard. And unfortunately, we don't know how to prove that those problems are hard for the most part, so we just make assumptions that we presume that it's not the case that everyone is insane and these problems really are hard. So this is the problem, decisional Diffie-Hellman. So what kinds of groups are we talking about? So in our implementation, which is written in Python, we have an implementation of a choice of group. You can either use ZP star for 2048-bit prime P, or you can use Dan Bernstein's elliptic curve implementation called curve 25519. A nice advantage of the latter is that, as we said before, when using elliptic curves, alpha can be just 32 bytes, okay, which is pretty short. And an important point is that there's only one alpha no matter how many hops there are. Okay? And we'll get back to that in a minute because that's a really important property of Sphinx. Okay, then beta, so that's alpha. Beta are the nested routing instructions. Okay, so it's the addresses written on the envelopes wrapped in the other envelopes wrapped in the other envelopes. Okay? And so it has both the identity of the next hop, the address of the next hop, and any of these parameters Alice might wish to communicate to the nodes as part of the mixing strategy. Okay, gamma is then a MAC of beta. MAC is a message authentication code. It's basically a secure cryptographic checksum to make sure that nothing has been modified in transit by an attacker. Okay, you probably know about MACs. And then delta is the multiply encrypted message payload. So it's the actual message encrypted, encrypted again, encrypted again, encrypted again, and each mix node will remove one layer of encryption. Okay? So how do we set up the system? We give each node a public-private key pair, and the way we do this is just the kind of standard way we do it for a system like El-Gamal. Every node picks a random secret key called X, or XN, for node N, and its public key is just G to the power of XN, where G is a generator of the group G, capital G, okay? And we call that YN. YN is G to the power of XN. So YN is the public key, and XN is the private key, okay? And then the way Alice shares some secret information, like the identity of the next hop, or these other mixing parameters, with any given mix node, is Alice picks her own random private key X. She computes alpha as G to the X, and computes the shared secret S as YN, the node's public key, to the power of X. Okay? And the node's public key YN is G to the XN. Let me point with the mouse here. So YN to the X is G to the XN to the X. Okay? Then the node N will receive alpha, can take alpha to the power of its private key XN, and get alpha to the XN, but alpha is G to the X, so that's G to the X to the XN, and you can see that G to the XN to the X equals G to the X to the XN, by just the properties of exponents. Okay? And now, so this is just the standard El-Gamal, Diffie-Hellman type thing going on. If you've studied cryptography, you'll have seen this before. And then S is a shared secret that can be used for whatever, symmetric key encryption, MACs, anything like that. Okay? So this is how Alice shares some secret information between her and any given mix node. Now, Alice has to share secret information with not just one mixed node, but our mixed nodes. Okay, 3, 5, 10, something like that. So how does she do it? The traditional way is that Alice just picks separate x's and produces separate alphas, one for each node. Okay? And this is the way that most previous mixed formats have worked, and is why their headers are so big. Because these group elements G, they're, for example, 256 bytes if you're using the mod n construction, and 256 bytes times 5 or 10 is already a kilobyte or 2 kilobytes. Okay? Just the alpha parts are taking up everything. So, can we get rid of that? Well, one thing you can do is there's no reason that Alice has to use a different alpha with each node, is there? She can just use the same alpha, but derive different shared secret keys, because she'll be taking the alpha, she'll be taking yn for the first node to the power of x to get her first secret key, yn for the second node to the power of x to get her second secret key, and so on. So all the secret keys will be different, but the alpha can stay the same. Why doesn't that work? Well, consider again. Remember, the whole point of this is to prevent an attacker from being able to link the incoming messages to the outgoing messages. Okay? So if she uses the same alpha to communicate to the first node and the second node and the third node, then that alpha will appear on the incoming message. So the incoming messages will have one value of alpha from this person, a different value of alpha from this person, a different value of alpha from this person. Then the outgoing messages will have the same alphas, but in a different order. And then it's just easy to match up, oh, there's that alpha and there it is there. So this incoming message was this outgoing message. Okay? So we can't do that. It has to be the case that the values of alpha that go out of the mix have to be completely different from the values of alpha going into the mix. It has to be the case that you can't figure out which incoming matched which outgoing. So how do we accomplish this? And the way we do this is by a technique called blinding. So in blinding, each node blinds the value of alpha as it processes the message. And by blinds is a cryptographic technical term. It basically means randomizes, but in a determined way. Okay? So randomized but determined seems contradictory, but it actually has a very strict meaning. So basically it means that Alice and the node can both predict what the output alpha will be given the input alpha, but no one else can predict that. To everyone else, it looks random. Okay? So the way this works is that the node n changes alpha by raising it to the power of a hash of alpha and the shared secret s. So note that only Alice and the node know this shared secret s by the security properties of Diffie-Hellman. So those two entities can both compute what this hash of alpha and s will be, but to everyone else, it's the hash of something which includes a random component that they don't know, and then we invoke the mystical random oracle model and say a hash of something you don't know is just a random number. Okay? And so anyone else, you're raising alpha to the power of a random number, and since we're in a prime order group, raising something to the power of a random number makes a uniformly random group element. Okay? So to anyone else, it is really indistinguishable from random. Okay? So now let's just look briefly at how Sphinx processes a mixed message. So the first thing you have to do is check that alpha is actually in your group. Okay, so that's here. Let me use the pointer. So that's here. So for some groups, this involves a public key operation. So if you're doing things mod a 2048-bit number, you have to take an exponentiation to check whether you're actually in the group. For other groups like elliptic curves, you don't need to do much work at all. In fact, for curve 25519, you just basically have to check that alpha isn't all zeros. Any other string is fine. Okay? You don't have to check anything really for beta, gamma, and delta because those are allowed to be any bit strings of an appropriate length. So you just have to check that their lengths are fine. So I didn't even write that down. The next step is to compute the shared secret. So you have alpha, you being the mix, have your own secret key xn here, and you take alpha to the power of xn to get your shared secret s. Okay, your shared secret s is then used in this MAC. Remember, there's a cryptographic hash, and the cryptographic part is that it uses this secret, S, to check that this gamma is really a MAC of beta. Okay? And if it is, that means no one has messed with the header. Okay, we'll talk about how to handle the payload in just a bit. Assuming no one's messed with the header, you can then process it. So now you have to decrypt the header, but you have to do it in such a way that the size of the header coming in matches the size of the header going out. And this is a little tricky because decryption necessarily removes some information, right? Necessarily, we're going to have some information in there like the size of the node, like the next MAC and stuff like that. And that necessarily removes some information. So how is it we're going to get this header to be the same size after as it is now? And the way, back to the picture here, is that we take the beta and we stick some extra zeros at the end. And with the parameters I was talking about, you stick 32 bytes of zeros, basically double the security parameter. And then you decrypt it, and you decrypt it with your favorite stream cipher. Okay, in our implementation, we used AES encounter mode. That's a lot of people's favorite stream cipher nowadays. Could use RC4. That was people's favorite stream cipher several years ago. Whatever you like. As I said, we use AES encounter mode, which is just you take your message and you XOR it with the encryption stream, and you get some result. Then you chop off the first bit, and that's the node, and prime is the address of the next node to send it to. If there were any other mixing parameters, that's where you would stick them. The next bit is gamma prime, that's the next MAC, and then the last bit is beta prime. Okay? So we extract those values. The next thing is you blind alpha here, like I said before, to get alpha prime. And then you have to get delta prime. The way you do that is you take S as your secret key and you decrypt the payload using S to get the next payload. And the way you decrypt it is by using what we call a large block cipher. So this is a block cipher like AES, but AES has a block size of 16 bytes. Okay? Bigger than older block ciphers like DES, but we're going to say we want a block cipher whose block size is the entire size of the message. And then we just do one block operation to do the decryption. Okay, and there are a number of constructions for such things. We use one called YNS by Anderson and BM in our implementation. So now we have all the primes, alpha prime, beta prime, gamma prime, delta prime, and we send that on to n prime. Okay? I'll just finish up the last couple minutes by talking about the proof of security. So in Crypto 05, Kamenish and Lisinskaya had a paper which gave 4 properties of an onion routing system that when taken together prove the system is secure, okay, in a particular model called the Universal Composability Framework. And what this proves is that the cryptographic format itself doesn't leak information. Now, you can still leak information if the mixing strategy is bad, but that's the fault of the mixing strategy. So we just say, mixing strategy is what it is. We're just not going to leak any additional information just from the mix format. Okay? Here are the properties. Correctness, this is obvious. The protocol has to work if there's no one attacking it. Okay? Your users would complain if it didn't. Integrity, this is a technical condition. It basically says there's an upper bound to the number of honest mix nodes that'll process a message. So the adversary can't construct a message that will go forever in a loop through your system. It will have to come out eventually. Okay? And this has to be true even if the adversary knows all the private keys in the system. Okay? So it's a somewhat strong condition. Then is wrap resistance, which is even stronger. This is even if an adversary can choose a node's private key, it can't construct a mix message that that node will process to produce a specific desired mix message. Okay? Again, another technical condition. Security is the important one. Security here is the usual indistinguishability game. So you have two messages with paths that go through an honest node. The challenger creates a Sphinx message out of one of them, and then it's the job of the adversary to determine which one. Okay? It's the usual kind of like in CPA game that we see in cryptography. Okay, so these are the four properties, and we prove that Sphinx has all these four properties. We also prove a fifth property, indistinguishability of replies. So what we do here is we take the security game, where the adversary can construct two different messages and paths through the network, but he can also, at his option, choose one of them to be a forward message and one of them to be a reply message. And then if I make this corresponding Sphinx message and hand it to you, and you can't even tell whether it's a forward message or a reply message, then clearly we have indistinguishability of replies. Okay? I won't go into proof details here, of course. I'm pretty much out of time, so see the paper. So just to wrap up, we've presented Sphinx, a new mix format. It has all the nice properties we want, provably secure, compact, supporting indistinguishable replies, and is computationally cheap. Thank you very much.
Yeah, that's kind of, you brought up one problem with separating out replies, and it's almost a comment, but I'd just like to hear your take on this. Is when you said if you can separate out replies from original messages, this reduces the size of your anonymity groups. But given that a reply is tied to a source message, this would imply that there's actually additional weakness coming out of it, possibly.
That's a very good observation, and there's been recent work over the last 3 or so years on exactly that issue, that even if replies are indistinguishable, you still might be able to gain some information just from the fact that if Alice sent a message to Bob, and then Bob sends a message shortly thereafter, it has a higher than average chance of going to Alice, right? And so, yes, there is additional information that comes from traffic analysis at a higher level. But we don't want to add to the adversary's ability by tagging messages as replies and forward messages. Exactly. Mike? Push your button.
On the front. Yeah. My question is, how far do you think is
This from like deployment.
How far is it from deployment?
I mean, what is the main impediment to
Of course.
full deployment?
Yeah, so we have an implementation, and we designed our implementation so that it will plug right into MixMinion, which, as I said, is a deployed network. So all we need to do, in kind of little scare bunny quotes here, is get that implementation together, and then convince the MixMinion people to basically upgrade to Sphinx. How easy that will be remains to be seen. Luckily, we know the MixMinion people. They're good friends of ours. So we'll see how that goes. Thank you very much.